Oh, drat these computers. They're so naughty and so complex. I could pinch them.
What's up, everyone, and welcome. In this episode, we're going to talk about SQL injections. According to analysis from EdgeScan, over 50% of all attacks in 2020 were SQL injection attacks. The most recent would be the WordPress statistics plugin SQL injection attack that affected 600,000 websites. But there are tons of examples you can sift through, including healthcare.gov back in 2013, FreePic/FlatIcon, that affected 8.3 million users, the WordPress WooCommerce plugin, Tesla in 2014, Cisco in 2018, Fortnite, Sony, and even MySQL themselves suffered from a SQL injection. In 2017, a Russian hacker dubbed Rasputin used SQL injection to penetrate the U.S. Election Assistance Commission, 24 U.S. universities, including Virginia Tech, Cornell University, Purdue, 10 U.K. universities, including Cambridge, Oxford, Edinburgh, and a wide variety of U.S. government institutions, like the Oklahoma State Department of Education and the Department of Housing and Urban Development. SQL injections is what we want to talk about today. Before we get in to the details, let's look at the agenda. We're going to start off with a definition. What is SQL injection? In order to build a good defense, we must intimately know our enemy. We're then going to move over to the anatomy of the attack. How does it work? If we know the pieces and how they work, we can evaluate where we are vulnerable. We want to learn from the fallen. Who has been attacked? We're going to review some notable companies affected, what their response was, and see if we can determine what their weakness was and evaluate its place within our organization. Finally, we are going to look at what can I do? Steps to improve. We're going to look at how we can implement measures to either fix for good and or continuously scan our systems to ensure this doesn't happen to us. So, what is a SQL injection? SQL injection is a code injection technique used to attack data-driven applications in which malicious SQL statements are inserted into an entry field for execution. The execution could be dump the database contents to the attacker. The SQL injection must exploit a security vulnerability in the application's software. So it's not directly going to the database. You have to find a vulnerability in, let's say, your web application, like a website. For example, when the user inputs is incorrectly filtered for string literal escape characters embedded in SQL statements, or the user input is not strongly typed and unexpectedly executed. SQL injection is mostly known as an attack vector for websites, but it can be used to attack any type of database, as we're going to see when we talk about the Fortnite attack. SQL injection attacks allow attackers to spoof identity, tamper with existing data, cause repudiation issues such as voiding transactions or changing balances, allow the complete disclosure of all data on the system, destroy data, make it otherwise unavailable, and become administrators of the database server. It's important to know that there are essentially three categories of SQL injection. There is what's called inbound SQL injection, or classic. There is inferential SQL injection, also known as blind. And then there's out of bound. In the classic SQL injection, the attacker implements the same channel of information to launch their attacks and to find the results. Inbound SQL injection simplicity and effectiveness make it one of the most popular types of SQL attacks. There are two methods which are sub-variations of this method. One is called error-based SQL injection, the other is called union-based SQL injection. In error-based SQL injection, basically, is from the name, the attacker executes actions that make the database display error messages. The attacker can probably use the data provided by the error messages to collect data about the structure of the database. In union-based attacks, the attacker makes use of the union SQL operator, which combines multiple SQL statements produced by the database to make a single HTTP response. This response may include data that can be leveraged by the attacker. In inferential SQL injections, also known as blind, the attacker sends data payloads to the system server and observes the reply and behavior of the server itself to get more information about the database formation. This method is called blind SQL injection because the data is not given from the website database to the attacker. He's essentially blind. He doesn't really know what he's seeing. Therefore, the attacker cannot see the server data or information about the attack in band. Blind SQL injections rely on the reply and the behavioral patterns of the server itself, so they're typically more difficult to perform, but they may be just as dangerous. Blind SQL injections generally categorized as follows. There's Boolean, and then there's time-based. In the Boolean attack, it sends a SQL query to the database, basically asking for a result. Give me back a result. The result will diverge depending on whether the query is true or whether the query is false. Based on the result, the information within the HTTP reply will change or stay unchanged. The attacker can then work out if the message generated a true or a false result. For example, let's say we wanted to know if the database contained a users table. If it contained a users table, I would get a true. If not, I would get a false. A time-based attack, is used to send a SQL query to the database, which causes the database sort of to delay for a couple of seconds before it can respond. The attacker can see from the time the database needs to react whether a question is true or false. Is there a user with a name admin? Yes or no? Based on the outcome, an HTTP response will be created directly or after a short period of time. The attacker can therefore work out if the message they applied returned true or false without relying on any data from the database. And the final category, called out of band, if you were to compare in-band and blind SQL injections, out of band SQL injections, it exfiltrates the data through an outbound channel, either DNS or HTTP protocol. The capability of a database system to initiate outbound DNS or HTTP requests may need to rely on the function available. The function can either be some kind of file operation function like load file, or it could be some kind of connection function like util HTTP request. Now, to exploit the out-of-band object SQL injection, the targeted web and database servers should fulfill the following conditions. So you have to have lack of input validation on the web application. You have to have network environment that allows targeted database servers to initiate outbound requests, either through DNS or HTTP, to public endpoints without restriction. You need to have sufficient privileges to execute the necessary function to initiate the outbound request. So you have to have elevation of privileges. So why would anybody use SQL injection? SQL injection attacks are inexpensive and easy to execute. Low-hanging fruit. The aftermath can be disastrous for victims. Undoubtedly, this method remains popular among hackers. As most of applications today are data-driven and accessible over the web, SQL injection flaws are inevitable and easily exploited. So, low-hanging fruit. Moreover, the growing popularity of shared database infrastructure has enabled hackers to abuse SQL injection vulnerabilities, impacting applications that share the same database. So it's sort of cross-poisoning. If let's say you were using your root user for accessing the database, and I use a vulnerability, I have then access to the root user. I can then attack all databases databases that are on that system itself. I use the same information because I have root. So in SQL injection attacks, perpetrators easily extract and disclose sensitive data. They erase database content, they forge identities, they alter transactions, and force privilege escalation to become administrators of the database server. So if I can become an administrator of one server, I can then most likely fiddle around and look throughout the network and try to escalate my attack to other servers, which we will see in the 7-Eleven attack. So how does it work? SQL injections can occur through user input fields, cookies, HTTP headers, as well as what are so-called second-order SQL injections. The basic SQL injection attacks, the most common, are through the use of user inputs. So as you see here, I have this very ugly-looking login form. Using it legitimately, I would put in a username, whether admin or user123, and then I would put in a legitimate password and click on login, because I want to access my account for some reason. So it's a legitimate use. Malicious use and try to exploit it through SQL injections, could put any kind of query in there I would want to meet my means or meet my end. In this particular example, this screenshot, you see that I'm trying to drop a table called test logins. Now, if the value here is not validated, when I press submit, and if the values are just taken and dumped into a SQL query and then executed and not sanitized or validated, or that it's legitimate, then and a table test logins existed, that table would be deleted. So it's also important to keep in mind the different variants of the SQL injection, how it can be executed, how it can be used. As I've said a couple times, there is the most common, which is the user input. Basic SQL injection attack uses user inputs. Web applications accept inputs through forms. Login form, registration form, contact form, comment form, etc. These pass users' input to the database for processing. If the web application accepts these inputs without sanitizing them, an attacker can inject SQL statements via form fields and delete, copy, or modify the contents of the database. But SQL injections can also be based on cookies. Another approach to SQL injection is modifying cookies to poison database queries. Web applications often load cookies, and use their data as part of database operations. A malicious user or malware deployed on a user's device could modify cookies to inject SQL in an unexpected way into the backend database. But wait, there's more. SQL injections can also be done through HTTP headers. Server variables such as HTTP headers can also be used for SQL injection. If a web application accepts inputs from the HTTP headers, fake headers containing arbitrary SQL can inject code into the database. Finally, we have second-order SQL injection. These are possibly the most complex SQL injection attacks because they may lie dormant for a long period of time. A second-order SQL injection attack delivers poison data, which might be considered benign in one context but is malicious in another. Even if developers sanitize all application inputs, they could still be vulnerable to this type of attack, so be careful. So let's look at an example. Now I'm going to cheat here. I'm only going to show you one example, and it's based on the most common attack, which is the classic or in-band. You're going to have to wait for another episode for me to go deeper into the out-of-band as well as the reflection or blind attacks because they're much more complex. But all of the principles in terms of mitigation apply based on this most common one. So if you implement my my recommendations at the end of this video, it covers all three. But I'm definitely going to come up with another episode that goes deeper into SQL injections because it's important considering it covers 50% of all attacks from 2020 and it's just growing. So you have your website, paid $1,000 for a beautiful design, you got developers to integrate it, you have this wonderful login form. You may or may not think it's wonderful depending on your taste, but so you have your website, and some attacker comes by, some perpetrator. He discovers your website, and he discovers that it has a vulnerability that enables SQL injection. For example, your login form. What does he do? He injects the website form fields with SQL, say username equals random user, and then or 1 equals 1, and password equals wrong pass, or blank equals blank, and blank is essentially always equal to blank. So he injects that. Now your vulnerable website does not sanitize these input fields, so it just adds them to the database query. So before we go into the malicious one, let's look at a legitimate query. Legitimate use of this form for logging in, I would put in my username. Let's say it's philcrack123, and my password, which you should never use, ever, is 1234567. That would be a legitimate query that would go to the database and it would select star from users where username is philcrack123 and password equals 1234567. It would return, it would make a database, a password comparison. Hopefully the password is encrypted, MD5, let's say, instead of 1234567. And it would make a comparison, and if that matches, then I would be logged in. I'd be able to see all my wonderful account information, all the money I spent on this website, or all of the information I've added, my forms, everything, right? Now, if that is not, if the form field values are not sanitized, what I type in here would be directly injected into the SQL query, creating here this example of select star from users where username equals admin or 1 equals 1. And then potentially and password equals wrong pass or blank equals blank. So this is 1 equals, I'm saying select star from users, which is select everything. All fields that are in the database, or columns, as well as all other values that match this query. So since 1 is always equal to 1, it would return the entire result list. And then, bada bing, bada boom, the perpetrator now has access to the entire list of user information from the database. So that's our example. Again, our forms do not, when we submit them, the processing of form information does not sanitize, does not check, does not validate what somebody typed in. Somebody could type in, "I am the greatest in the world," and that would just be passed through. They could type in, "delete everything, delete every database file," whatever, and that would just be dumped right into the SQL query without validating it. And if it's malicious SQL code, then that would either that would be processed with the SQL query itself, and could potentially delete the entire database or return all information, which could be things like credit cards information, usernames, passwords, telephone numbers, email addresses, everything, right? So let's look at some known cases and see what we can glean from them. We're going to start off with 7-Eleven. Goes back a little while, 2007. Russian attackers, evidently using a SQL injection vulnerability, they gained unauthorized access to 7-Eleven Incorporated's servers through their public-facing internet website. They then leveraged that access to get into servers supporting the ATM terminals that are located in the 7-Eleven stores. So this access caused 7-Eleven to basically shut down their website on November 9th, 2007. So what did they do? They found a SQL injection vulnerability on the website. They then gained access to the website, so they filtered around and looked in the network, saw other servers. They then were able to get access to those other servers, and those servers controlled ATM terminals. At the time, there were 5,500 Citibank ATM terminals at 7-Eleven stores around the country. According to SEC documents, 7-Eleven ran its own transaction processing server to handle 2,000 of them, and they have advanced models called VCOM machines manufactured by NCR. The 7-Eleven VCOMs support special functions like bill payment, check cashing, and money order purchases. For 2 weeks in September 2007, anyone who typed in their PINs in those machines were exposed. So again, through, I don't know if it was a WordPress website, Drupal, Joomla, whatever, but through a vulnerable website, the attackers used SQL injection. They got access and most likely control of that server. Through access and control of that server, they were able to then gain access to other servers, and those other servers, in 7-Eleven's case, supported ATM machines. So they were able to exfiltrate all data about people who entered in their PINs to those ATM machines that were running that VCOM software. Next, we're talking about Tesla. Yes, Tesla. They had a blind SQL injection found in 2014. They got lucky because BitQuark found and reported this vulnerability. It was located in their Tesla Motors design studio. If you don't know what it is, the design studio is kind of a nice tool that lets you customize your Tesla before you order it. It gives you the option to share your creation with others with using a unique link, which Tesla generates. So, like share on Facebook or share on WhatsApp or Tinder or wherever you want to share it. Share it via email. Now, usually those links to these kinds of customizable online tools, they have all of the things you entered in part of the query string, like color equals black, and number of doors equals 4, a model equals blah blah blah, right? So that's all part of the query string. So it's super long. Well, Tesla then integrated a URL shortener, kind of like Bitly, if you're familiar with Bitly, to shorten those URLs to make them more readable, or make it look nicer in Twitter if you post it to Twitter, or so your grandmother can just type it in instead of clicking on the link if she doesn't know how to do that. Whatever the case is, the reason is they added a URL shortener. Now, it was in this external URL shortener script, or this self-added or self-developed URL script, that the SQL vulnerability was found, giving access to Tesla's backend database, including access to all online customer records and admin access to the site. So during the testing, it was noticed that this script behaved a little differently depending on the input, and when they investigated, it was using some different injecting of some quoted strings. They played around a little bit, and then they found that there was a standard blind attack vector with this example plus sleep 10 plus. So again, public-facing website. They had a tool. That tool allowed you to kind of customize your Tesla, and then they had a sharing function. The sharing function had an additional function to shorten the sharing URL. That URL shortener script had the SQL injection. Finally, for today, we're going to look at Fortnite. 2019, Checkpoint researchers discovered multiple security vulnerabilities in Fortnite, which, if you don't know, it's a massively popular online game with over 80 million users worldwide. The reported Fortnite flaws, 80 million users, a huge company, making tons of money, right? The reported Fortnite flaws included SQL injection, cross-site scripting, a web application firewall bypass issue, and most importantly, an OAuth account takeover for a vulnerability. So they had quadruple flaws. They had 4 separate flaws that found at once. According to the researchers, the combination of cross-site scripting and malicious redirect issued on Epic Games subdomains allowed attackers to steal users' authentication token just by tricking them into clicking a specially crafted web link. So if you've seen my episode on cross-site scripting, you know how dangerous that could be. Here, they had not just cross-site scripting, but they also had the SQL injection, and they had a firewall bypass issue, and they had an OAuth token takeover vulnerability. Once compromised, an attacker can then access players' personal information, buy in-game virtual currencies, and purchase game equipment that would then be transferred to a separate account controlled by the attacker and resold. So you can imagine that they used your account to buy a bunch of stuff, and then they used the SQL injection to change the database so that that stuff no longer belongs to you, it belongs to them, and then they resold it. The attacker even could have access to all the victims' in-game contacts and conversations held by the player and his friends during the game, which can then be abused to exploit the account owner's privacy. So let's see how it worked. The attacker first sends the victim a malicious link. The victim unwittingly clicks on the link to the login page. Now, within the link, there is a malicious redirect, which we'll see in a minute. If you ever think when you click on a link to go to my account, but you're not logged into a website, you first log in and then all of a sudden you're automatically redirected to your my account once you're logged in. Well, this is the same type of attack. That malicious redirect, but didn't bring you directly to your my account. It brought you to an external website. So you click on this link, you use the single sign-on, like Facebook or Google and any of the other applications that they had integrated here. Once you're signed in, the malicious URL with that redirect redirects you to the attacker's malicious URL, where they have this malicious JavaScript, which basically says, "Oh, I don't have the token. I don't remember it. Can you send it again?" So the token is then reissued and is passed through to the attacker. He then has access to your account. So here's a screenshot showing the code with the sort of, I guess it's base 64 encoded information here, and then they de-encoded it, and you could see here the redirect URL that's passed through is not sanitized, is not proofed. So if your application accepts redirects, as I mentioned before, like to my account, you should be doing a domain check. You should be checking that redirect URL, that is a valid URL in your domain, and not sort of bouncing the person back off your system with the login credentials to go to some external site. So those are the examples we're going to gone through today. Showed you how they were attacked, what the flaw was, what the vulnerability is, and you can judge for yourself whether it affects your system. Now we get into how do you stay safe. The first thing I say is get yourself a web app firewall. Any kind of firewall. One of the best practices to identify SQL injection attacks is having a web application firewall. A WAF, as it's called, operating in front of the web servers, monitors the traffic which goes in and out of the web servers and identifies patterns that constitute a threat. Essentially, it's a barrier between the web application and the internet. A web application firewall operates via defined customizable web security rules. These sets of policies inform the web application firewall that weaknesses in traffic behavior it should search for. So based on that information, a WAF will keep monitoring the applications and get the get and post requests it receives to find and block malicious traffic. The value of a WAF comes in part from the ease with which policy modification be enforced. New policies can be added in no time, enabling rapid rule implementation and fast incident response. So it might not catch everything, but when you monitor it, you can catch it early enough to have a fast response. WAFs provide efficient protection from a number of malicious security attacks, such as SQL injection, cross-site scripting, session hijacking, distributed denial of service attacks, cookie poisoning, parameter tampering. Along with these benefits, a WAF also offers automatic protection from varying known and unknown threats, with not only strong default policies, but also fixes for your specific WAF architecture. Real-time application security monitoring, and robust HTTP traffic logging that lets you see what's happening instantly, in real time, essentially. Considering the benefits even beyond preventing SQL injection attacks, a WAF should always be considered a part of a web security defense in-depth strategy. The second thing I would say is avoid admin privileges. Don't connect your application to the database using an account with root access. This should be done only if absolutely needed, since the attackers can gain access to the whole system. Even non-administrative accounts server could place risk on an application, even more so if the database server is used by multiple applications and databases. For that reason, it's better to enforce least privilege on the database to defend the application against SQL injection. Ensure that each application has its own database credentials and that those credentials have minimum rights an application needs. Instead of trying to determine which access rights you should take away, focus on identifying what access rights or elevated permissions your application needs. If a user only needs access to some parts, you could create a mode that strictly serves this function. So now we're going to get into the specific things about your SQL queries and how you can modify them, manipulate, and improve them. So with user input channels being the main vector for such attacks, the best approach is controlling and vetting user input to watch for attack patterns. Developers can also avoid vulnerabilities by applying the following main prevention methods. Input validation. The validation process is aimed at verifying whether or not the type of input submitted by a user is allowed. Input validation makes sure it is the accepted type, length, format, and so on. Only the value which passes the validation can be processed. It helps counteract any commands inserted into the input string. In a way, it's similar to looking to see who is knocking before opening the door. Validation shouldn't only be applied to fields that allow users to type an input, meaning you should also take care of the following situations in equal measure. Use regular expressions as whitelist for structured data, such as name, age, income, survey, response, zip code, to ensure strong input validation. In the case of fixed set of values, such as drop-down list or radio buttons, determine which value is returned. The input should match one of the offered options exactly. So you should also do database table validation. So here's an example of how you could do switching case to say the table name to do database table validation. If it doesn't match, you send back an error. You want to parameterize your queries. Parameterized queries are a means of precompiling a SQL statement so that you can then supply the parameters in order for the statement to be executed. This method makes it possible for the database to recognize the code and distinguish it from input data. The user input is automatically quoted, and the supplied input will not cause the change of the intent. So this coding style helps mitigate a SQL injection attack. It's possible to use parameterized queries with the MySQLi extension. If you use MySQL, PHP 5.0 is long gone, but it presented a better approach when working with databases. The PDO adopts methods that simplify the use of parameterized queries. Additionally, it makes the code easier to read and more portable since it operates in several databases, not just MySQL. Here is an example of parameterizing the actual value of the variable ID. Here they're using get. I wouldn't necessarily be submitting forms or getting information out of a query string. You see where ID equals ID, and then you see that you bind the parameter of ID to the variable ID. This code uses PDO with parameterized queries to prevent the SQL injection vulnerability. As I said, I'd go further. I would only use post so that you don't show all of your variables in the query string. And I would also go ahead and verify that the ID is of type X, for example, a number. Otherwise, I would throw an error. This means ID equals wrong user or 1 equals 1. It wouldn't even get to the query stage because it would be throwing an error as an invalid type. So I wouldn't be wasting resources connecting to my database. If somebody was, let's say, trying to flood my database with these types of queries, it wouldn't even get to the database. It wouldn't even put it under any kind of strain. So now we can go into stored procedures. Using stored procedures require the developer to group one or more SQL statements into a logical unit to create an execution plan. Subsequent executions allow statements to be automatically parameterized. Simply put, it's a type of code that can be stored for later and used many times. Here's the example of how to create a stored procedure, and then you could parameterize your variables before you pass it through the stored procedure. Escaping. Always use character escaping functions for user-supplied input provided by each database management system, DBMS. This is done to make sure the DBMS never confuses it with the SQL statement provided by the developer. Previously, your code would be vulnerable to adding an escape character in front of the single quotes. However, having this small alteration will protect against an illegitimate user and mitigate SQL injection. As you can see here, I'm using the MySQL real escape string in this example. You would use the respective one for your database. So, that's it. SQL injections in a nutshell. We went through an example of the most widely used case, which is the classic variation or in-band variation. In future episodes, I will be talking about the out-of-band as well as the reflective or blind SQL injection. I hope you learned something. I hope you could take some of these points and implement them, or at least verify and make a checklist and show it to your boss or show it to whoever your client may be and say, look, we are highly secure against SQL injections. I appreciate you watching. If you like the video, don't forget to give a thumbs up. Don't forget to subscribe if you are not already subscribed. I'm going to be bringing out a number of other videos, not just about all of these vulnerabilities that I've been doing recently, but also going deeper into DevOps, how you can improve your game, how you can improve your processes, your workflows, setting up systems, whether it's Gitio, like I showed in one of my episodes, or your own Jenkins system for your pipelines and workflows. All of those types of great applications and great processes so that you can become more efficient, stay secure, keep your development and your systems as secure as humanly possible. So again, thank you, and look forward to seeing you on the next episode. Take care.